Vantov factor. So Vantov factor comes in with colligative properties. Now it's important to remember with colligative properties that the identity of the solute doesn't matter. It's only the total moles of solute per kilogram of solvent. But what happens is that ionic compounds will dissociate in a polar solution. Because these are homogeneous solutions, if I have an ionic compound, the assumption is that you have dissociated the ionic compound. So the Vantov factor takes that into account, and the Vantov factor will be the number of moles of ions created per moles of ionic compound. So I just plug that into my delta T expression. So delta T is equal to the I, Vantov factor times KBM, or KFM, depending on if I'm looking at boiling point elevation or freezing point depression. It would also go in when you're looking at vapor pressure lowering. You're multiplying it by that Vantov factor, as well as osmotic pressure. So anytime you have any sort of compound in which you have dissociation and you're working with colligative properties, you have to take into account the Vantov factor. So the first example is just looking at boiling point elevation. So I have the boiling point elevation change for a solution that has sugar dissolved in water versus the same amount of magnesium nitrate, or actually less amount, in more water. So the 2 moles of sugar, it's not an ionic compound, it's a polar compound. When I have 2 moles of sugar, I will end up with 2 moles of sugar dissolved. So there is no Vantov factor. And so the molality of that will be the 2 moles of sugar over the 0.4 kilograms of solvent, which will be a 5 molal solution. No dissociation, so my Vantov factor is equal to 1. So delta T is equal to KBM, or 2.56 degrees Celsius. So my new boiling point will be 2.56 degrees Celsius above the normal boiling point of water, which is 100 degrees Celsius. However, if I have my magnesium nitrate solution, magnesium nitrate in water will dissociate completely into 1 mole of magnesium plus 2 ions and 2 moles of nitrate ions. So in total, the number of moles of ions created per mole of magnesium nitrate is 3. So the Vantov factor is 3. So the molality of this will be equal to 1 mole of magnesium nitrate over 0.6 kilograms, or 0.6 molal. But because I have the Vantov factor in my equation, it will have 3 times the effect of just 1 mole of a regular non-dissociating compound. So in this case, my boiling point will increase by 0.912, and my new temperature will be 100.912. So even though I'm dissolving half the amount in more water, it will still have an appreciable effect on the boiling point of the water because of the dissociation that occurs. This is also the reason why we put salt on roads when we are trying to lower the freezing point, because of the dissociation of the salt. So if I take a salt like magnesium nitrate, as opposed to putting sugar on the road, I will get 3 times the lowering of the temperature of my freezing point rather than if I'm putting sugar on. And sugar is also very sticky. Example B, this is looking at the change in vapor pressure. So I have a change in vapor pressure of 2.5 moles of sodium chloride dissolved in 0.8 kilograms of water if the initial pressure is 800 torr. So when I dissociate, I realize that I create 2 moles of ions, so my Vantov factor is equal to 2. So I'm looking at my change in pressure, which is my molality, my mole fraction, of my solute times my original pressure times the Vantov factor. So 8 kilograms of water, as I run this through, is 44.4 moles of water, and I have 2.5 moles of sodium chloride, so the mole fraction of sodium chloride will be 2.5 over the total, 44.4 plus 2.5. And then I multiply that mole fraction times my Vantov factor times the original pressure. And I see that my vapor pressure lowering is going to be 85.3 torr lower. So my new vapor pressure would be 800 minus 85.3 torr. So remember that this change in pressure is always going to be lowering because it's vapor pressure lowering. The solute that's at the surface prevents the number of molecules of water that would normally evaporate from evaporating. So as a result, there is fewer molecules in the vapor stage. And the final one is looking at it for osmotic pressure. So if I want to find the osmotic pressure of 0.4 moles of magnesium chloride dissolved in a total of 0.6 liters of solution at 27 degrees Celsius, my Vantov factor here is going to be 3 because magnesium chloride dissociates into 1 mole of magnesium ions and 2 moles of chloride ions. So I plug this into my pi equals MRT, but I also have to multiply by my Vantov factor. 3. My molarity is going to be equal to 0.4 over 0.6 times R. And then I have to remember to convert my temperature to Kelvin. So 27 plus 273. And I get a osmotic pressure of 49.26 atmospheres. So what happens in the spring is that oftentimes what plants will do is that they will absorb salts into their tissue to raise the osmotic pressure so that more water comes into the roots and is able to drive the sap up the tree, because sap is mostly water. So by changing the molarity and using salts instead of just sugars, dissolved sugars, plants are able to control that. Plants will also do the same thing for freezing point depression. They will exude out salts into the soil around it, thereby decreasing the freezing point of water, defrosting the soil around it so that it can uptake water, because plants can only uptake water in a liquid form. And this is what enables them to grow even when there's snow on the ground. So clues that you have to use the Vantov factor is that you have an ionic compound being dissolved. It's a reactant. So then you have to find the Vantov factor, which is just dissociating that ionic compound. Now in real life, the Vantov factor is usually lower than the ideal, and it's experimentally determined. So that's something that we just have to run experiments for and put the actual Vantov factor for. But putting it in the ideal situation still gives you the same idea that ionic compounds, or anything that dissociates to create more particles, is going to affect the colligative properties, any of the colligative properties that we're looking at.